Welcome everyone to our IAQM webinar, assessing the synergies between net zero strategies and air quality in the UK. Today we are joined by Adam Brighty, who is a third-year PhD student at the Centre for Environmental Policy at Imperial College London. Adam's research focuses on the synergies between climate mitigation strategies and air quality in the UK. Today's webinar will talk about a rapid assessment model that has been created known as the Climate and Air Pollution Synergies Assessment Model, CAPSAM. The webinar will present the ongoing research that has been done using this model, looking at the model methodology, the assumptions required to assess future energy systems, and the key conclusions from the current work. As always, there'll be a chance to ask questions at the end of the presentation, so please pop these in the Q&A function at the bottom of your screen at any point during the presentation, and I will ask these on your behalf later. Thank you for logging in today, and I'll now hand over to Adam.
Perfect. Thank you very much, Derek. Thank you to everyone at the IAQM for joining this. I really do appreciate it. And also Eid Mubarak to anyone that's celebrating today. As Derek said, I'm Adam Brighty. I'm a third-year PhD student at Imperial College London, working with Professor Helen Apsimon. And I'll be talking today about assessing the synergies between net zero strategies and air quality in the UK. So just as a brief overview of what we'll be going through today, we'll do a sort of introduction and a sort of key message. We will go through some background and some context about why we're doing this research, why it's important. And we'll also talk about the model that we've been producing in order to put this research into practice, which is known as the Climate and Air Pollution Synergies Assessment Model. And then we'll show you sort of how it works within some sort of decarbonisation scenarios, sort of how the sort of outputs that CAPSAM can provide. And then we'll also do some future work as well, showing you what we're doing going forward. So just as a brief overview, as Derek said, my PhD title is What are the synergies between climate mitigation strategies and air quality in the UK? This sort of covers, as a very broad area, it covers a lot of different research directions and avenues effectively. So the first one that we typically look at is the decarbonisation direction for different sectors. So looking at use for electrification, hydrogen usage, carbon capture and storage, and biomass and things like that. We look at the new technologies that are going to be put in place in some scenarios and the spatial assumptions needed. One of them that I'll go into a bit of detail later will be the hydrogen production sector, which I've got a slide on later on. And then we also look at the air pollution abatement as well, so the emission factors that are expected for these new technologies as well. We also have a section on in my thesis about the synergistic pollutants, so pollutants that illustrate both climate warming abilities and deleterious health effects. Black carbon is one of those. If you breathe it in, it's very harmful, but it's also a short-lived climate forcer. But for today's presentation, we'll just be looking at kind of these three sections, just within the energy system, as that's sort of the scope of my research project. All this work is funded by Defra as part of the Support for National Air Pollution Control Strategies contract. So I should say thank you to them before we go any further. So just quickly as a key message, if anyone has to leave early, just trying, for the rest of us who are staying for the whole of it, to try and keep it in your mind going forwards, that decarbonisation provides a unique opportunity to achieve the twin goals of climate mitigation and improved air quality. So let's just keep that in our minds going forward if you can. In terms of background and context about why we care about air quality, I know a lot of people here probably know a fair bit about it, but some of you may not. We then asked about why decarbonisation is important, and then how we're typically investigating this. So in terms of why we care about air quality, according to the UK Office for Health Improvement and Disparities, poor air quality in the UK poses the largest environmental risk to public health. According to the Health Effects Institute, it's also the fourth leading risk factor worldwide to premature death, and in the UK it causes around, or contributes to around 36,000 premature deaths a year through links to poor lung development in children, asthma, dementia and diabetes, and also heart and lung diseases as well. In terms of why decarbonisation is important, is due to the fact that emissions of atmospheric pollutants such as PM2.5 and nitrogen oxides, or NOx, and then greenhouse gases are intrinsically linked by the combustion of fuels, whether that's fossil fuels, so oil, natural gas, coal, biomass, even municipal solid waste, and even hydrogen to an extent. They're all intrinsically linked. It's important for decarbonisation because, as you may or may not know, that the UK is legally required to reach net zero greenhouse gas emissions by 2050 in line with the UK Climate Change Act. So it stands to reason that the decarbonisation policies that we put in place will determine the extent of air quality improvement in the UK going forward. So we intend to investigate this by looking at the largest greenhouse gas emitting sectors in the energy system. So that's electricity and energy production, building heating, so both domestic and public/commercial heating, industrial combustion, and also road transport. We then investigate these different decarbonisation scenarios, so electrification, hydrogen usage, carbon capture and storage, and biomass usage as well. And then we assess these different areas on the greenhouse gas emissions, pollutant emissions, and crucially pollutant exposure, and the monetary benefits from reductions in pollutant exposure. Now, the main question that people could be asking here is, how do we actually intend to assess these air quality and climate impacts? And this is with the model that, as Derek said, that we've put together, which is called the Climate and Air Pollution Synergies Assessment Model, or CAPSAM for short, as it is a very big mouthful to say out loud, which does rapid air quality and climate analysis for decarbonisation scenarios. There are a variety of reasons why we've had to put this model together. The first one is if you're using an energy system model, such as the UK Times model, which is used by the Committee on Climate Change, Defra, the National Grid. These typically do not investigate air pollutant emissions. When they have investigated air pollutant emissions in the past in sort of an optimization framework, we have seen results that will allow for a more ambitious scenario because you've been able to account for the reduction in air pollution emissions and the savings that you make from there. Even then, I think the issue is that, or we would argue that the issue is that considering air pollutant emissions alone is not sufficient, as the location of air pollution emissions is crucial for assessing air pollution exposure. So, for example, if you have an emission source that's in the centre of London, say around Piccadilly Circus, compared to one that's in the Scottish Highlands, the one that's in the centre of London will have a much greater impact on pollution exposure. Not that the one in the Scottish Highlands is important, but again, the one that's in the centre of London will contribute more to that exposure level. Now, of course, if you have an air quality model, this isn't really going to be an issue for you, but it's very rare that people just have their own air quality model. You can't just create one out of nothing. It takes a lot of validation and time to do so. And they also require a lot of expertise to run and a lot of resources. They're very computationally intensive, and they're also very slow to run. You won't be able to do multiple scenarios across an entire time period of say 2020 to 2050. To do 30 runs would be very computationally intensive and would take a lot of time. So the compromise that we've come up with within our group is a quick and simple model that can give air pollution exposure estimates, not just emissions, we're looking at exposure as well. That's also suitable for multiple runs, multiple scenarios, and therefore good for doing uncertainty analysis and Monte Carlo simulations and stuff like that. And this is effectively what CAPSAM is. It's a very simple diagram of how it works. You would take your scenario data, for example. You would apply what we call emission factors to get our emissions on our emissions projections across a scenario. We then have this crucial next step, which goes beyond emissions to assess exposure. And we take something called impact factors from UKIAM, which is the UK Integrated Assessment Model, which I'll explain on the next page. But it's these numbers that effectively take us from just looking at emissions to being able to give us a slightly better spatial understanding of these of pollutant exposure and how the changes in pollutant exposure happen over an entire scenario, for example. Lastly, what we can then do with the model is we can take some benefits data, some monetary health benefits, and assess the monetary savings across a scenario based on the reductions in pollution exposure. So just as a sort of background and description, as I said, UKIAM is the model that is the main model that is used within our research group. It is a UK air quality model that maps pollutant concentrations on a 1 by 1 kilometre resolution. It's previously been used by Defra in their PM 2.5 target setting work. It's the report that's out, I believe, for about a year now or so. But again, it's a model framework that takes source receptor relationships from larger dispersion models such as EMEP, and also deposition data from FRAME as well. So it's a much larger model that we then take the impact factors from. It includes more than just the anthropogenic sources that CAPSAM has. It also includes natural and imported contributions and agriculture as well. But the model runtime is at least 30 minutes, and in a lot of cases, a lot longer than this if you're looking at more than one region of the model. What the impact factors are effectively a number that applies to each source and each pollutant within the model framework. And it's effectively gives you an idea of the contribution of an emission source to total pollutant concentration. So it's effectively how you would produce these is within UKIAM, you modify the emissions from each source, seeing how the contribution to pollutant concentration changes, and you interpolate between the lines in order to get the gradient, and that is what your impact factor is. So, for example, a large impact factor would be sources in urban areas, such as domestic heating with gas on the natural gas grid and road transport as well. And you'll have much smaller impact factors for those that are in rural areas, for example. And we've included these in CAPSAM to derive these source-specific contributions to pollutant exposure. We can then also do monetary health benefits as well. As I said, these are estimates of savings from reductions in air pollution exposure. We take these benefits numbers from Defra. They're on a pounds per person per microgram change in exposure basis. There is actually a wide range of values, as I will explain later, but we take the central ones. And in general, it's a much more accurate way of assessing the potential health benefits of a decarbonisation scenario than using emissions and an average damage cost, for example. And then across the scenario, you can get your pounds per person estimate for savings from the initial to the final year of the scenario. We can also apply year-on-year discount rates as well. As I said at the beginning, we've had to make some assumptions for some new technologies as well. There is some very limited spatial information on a lot of new sources that are potentially going to be part of our energy system going forwards. One of these large potential sources could be hydrogen production. The one that we're most concerned about in this case will be blue hydrogen production, as it would have some air pollution emissions in the same way that electrolysis potentially wouldn't. So what we've had to do is sort of try and find a proxy in the interim for blue hydrogen production within an energy system, for example. So what we have on the graph on the left here is the industrial decarbonisation strategy that BEIS, as it was then released in 2021, that had the potential points for carbon capture and storage clusters. So we've made the assumption that for blue hydrogen that is steam, methane reformation with carbon capture and storage, it will have to be placed in one of these clusters for it to be produced, for example. We've then looked at the different sources, I should say, that we have within the UK integrated assessment model to see which impact factors could line up well with the potential production points for blue hydrogen and hydrogen in general. We found that they matched up relatively well with the sources, the impact factor sources that we have for refineries, as you can see, is Southampton and Medway, and then Humberside and Grangemouth, and potentially Merseyside as well. So these are the sort of things we've had to do is to try and get some spatial information in the meantime as a proxy for blue hydrogen. In a lot of other cases, we can assume that things will stay relatively similar. Building heating will remain as building heating in the future. The domestic settings won't really change in their position too much. But yeah, these are the sort of assumptions that we've had to make going forward. So I appreciate that's a lot of information. So I thought it'd be good if we took you through some example scenarios. We've got some decarbonisation scenarios that we've taken from the national grid. The national grid is the UK's energy system operator, and on an annual basis, they're required to produce 4 decarbonisation scenarios of how they think we can reach net zero by 2050. So the scenarios range in the energy demand, the fuel mixes as well, and also the technologies employed, as well as the amount of engagement on the demand side. So this is taken straight from the national grid. We have 3 net zero scenarios and 1 non-net zero scenario. The first one that we have is consumer transformation. This is a scenario that uses a lot of electrification, but more crucially, there is a lot of consumer engagement. There is a lot of flexibility on the demand side, and there's a lot of energy efficiency to bring down overall demand. This is really key going forward as it will become apparent later on. We then have system transformation, which is kind of the other side of the coin. There's a lot of hydrogen, especially within the heating system, a lot of blue hydrogen production, and there's a lot less in terms of demand side engagement, and a lot of the flexibility is placed on that burden's been placed on the supply side, for example. We then have leading the way, which is sort of the best of both in this instance. You have a lot of engagement, but then a mix in your energy mix of both electrification and hydrogen within the system as well. And everything's kind of done a little bit quicker with that sort of lifestyle change as well. We then also have falling short, which is a non-net zero scenario. It's not quite business as usual, because there is some progress within sort of power and transport, but less so within building heating, for example. So what we'll just do now is a quick investigation of the different pollutant exposure contributions from the different sectors, and also the monetary savings from these sectors as well, and these different scenarios. So what we have on the left now, the contributions from the different sectors to nitrogen oxide exposure across the time period from 2021 in the initial year of the scenario to 2050. So we have electricity production in the top left, hydrogen in the top middle, and then top right we have domestic heating. We then have public heating and commercial heating, and then industrial combustion and road transport as well. And then we have the total of all of these six just at the bottom here. I think the first very important thing to note is that road transport in the initial year of 2021 is very, very dominant. Its contribution is over 6 micrograms per meter cubed of nitrogen oxide exposure, followed by the other two more urban sectors of domestic and public heating. Now, that shouldn't be a surprise too much, because nitrogen oxide is a primary pollutant, and it's typically felt by those in urban areas a lot more. And then we have the slightly more rural sectors where we're not getting that sort of similar contribution. Across the three net zero scenarios in the blue, the grey, and the sort of purpley colour here, what we can see by 2050 is that in a lot of these cases, these scenarios do seem to converge by 2050. But there is the interim years where we're seeing quite significant differences in some of these sectors. This is very important. This is the impact, as I said before, of these efficiency measures, and the reduction of demand early on and the consumer engagement can give you much earlier reductions in pollutant exposure or nitrogen oxide exposure than scenarios that don't have that sort of level of engagement. Again, for road transport, by 2050, as I said, we're seeing it dropping down to around a very, very slim contribution to nitrogen oxide exposure as a result of the phase out of internal combustion engine vehicles. And I think the other important thing to note here is for hydrogen production, what we're seeing, even in a scenario that uses a lot of blue hydrogen with our initial assumptions, it doesn't seem to be a massive contribution to nitrogen oxide exposure going forward to 2050, even in a scenario that uses a lot of blue hydrogen. And if we just look at the, across the total contribution here, we are seeing quite a significant drop in all of the net zero scenarios compared to the non-net zero scenario, for example. For PM 2.5 and particulate matter, it's a relatively similar story here. Again, road transport was initially dominant, but the two slightly more rural sectors of industrial combustion and electricity generation have a much more similar magnitude of contribution to PM 2.5 exposure as the more urban sectors of domestic and public heating. And this is predominantly due to the formation of secondary particulate matter in these instances. I think one of the most important things to note for road transport, again, is that unlike for nitrogen oxide, where we're seeing it tend towards zero, we're not, for nitrogen oxide yet, for PM 2.5, we're not seeing that same contribution to reducing to zero due to the remaining impact of non-exhaust emissions. Now, these are emissions from cars that are abrasive, so we're talking about road wear, tyre wear, and brake wear. When you have to brake heavily, go around a corner quickly, accelerate quickly, you're abrasing the road and your tyres and sometimes your brakes as well. So this is the sort of remaining contribution from a fleet of cars, which is predominantly battery electric vehicles and fuel cell electric vehicles as well. Again, especially what's notable for domestic heating is the impact of these efficiency measures in these early years makes quite a large difference in contributions to pollutant exposure in comparison to in 2050, where they seem to converge a lot more. And then hydrogen production, again, even in a scenario that uses a lot of blue hydrogen, we're not anticipating massive contributions to to PM2.5 exposure, even in a scenario that uses, again, a lot of blue hydrogen. But as I said, I think one of the most important things here is the impact of these efficiency measures in these interim years. So I thought it would be good to just illustrate that slightly further with some interim year sort of time slices. So we have a similar graph again. We've got 2021, 2030, and 2040 for the 4 different scenarios, and then the different sectors stacked upon one another. What we can see even, well, firstly, we can see the dominance of road transport decarbonisation. Again, it's hugely important going forwards for reductions in air pollution exposure. But even by 2030, we can see the impact that reductions in consumer demand in domestic and public heating can have in scenarios that have that sort of demand side engagement compared to one that relies a lot on the supplier side to figure things out effectively. By 2040, again, it's a very similar story. You can see domestic and public heating here have a much lower contribution to nitrogen oxide exposure than in a scenario that uses a lot more in terms of supply side flexibility. For PM2.5, it's a relatively similar story again. It's less noticeable in 2030 beyond domestic heating here. Public seems to be relatively similar. But then by 2040, you can again see the impact again of domestic heating and how much it can be reduced by having that sort of consumer engagement. And here we can see again that the importance of the non-exhaust emissions from road transport as well, that you won't remove unless you remove the entire transport fleet. But I don't see that. I don't think anyone sees that happening by 2050 at least. The last thing so that CAPSAM can do is it can calculate some sort of monetary savings from reductions in air pollution exposure. These numbers are taken from Defra. They include a year-on-year discount rate taken from the Treasury's Green Book that sort of encourages making savings earlier on in your scenario, for example. So, or your reductions in pollution exposure, I should say. So instead of making all your reductions in 2049 compared to doing it in 2025, you'll be saving a lot more money doing it in 2025 than much later on. So these are the numbers in pounds per person for reductions in nitrogen oxide exposure. We then have PM2.5 reductions in pounds per person and sulfur dioxide as well, and then the other environmental benefits that I can explain later. So as you can see, the most important thing in terms of on a monetary basis for reductions is road transport again, especially for reductions in PM2.5 and nitrogen oxide exposure and the money you can save from that. So just for context, a sort of savings of around £43 per person from road transport decarbonisation would give you a value applied to around 67 million people of around £2.9 billion. Now, as I said at the start, we're using the central benefits values here. The range could be about 10 times lower to around 4 times higher. So this is on a basis that you could be up to about £12 billion or down to 300 million. So something needs to be constrained a little bit, but these are the numbers that we're working with. As you can see, building heating also makes quite a large difference in terms of reduction in monetary savings, as well as electricity production and industrial combustion here. So I think the last thing to note is that you can see on the scale on the side of sulfur dioxide that the scale is much smaller due principally to the fact that we have pretty much reduced most of our sulfur dioxide already through pretty much the phase out of coal and heavy sort of oil as well. So there's not a lot of coal-fired power stations. There's not a lot of coal building heating either going on anymore either. But in general, what we can say is that the savings from reductions in air pollution exposure is in the order of billions, and these are sort of numbers that could be very useful for energy system optimization models to allow for increased ambition in your net zero scenario, for example, because you're making your savings elsewhere. The last thing I want to talk about today is the sort of future work that we're doing. Now, as I said at the start, that CAPSAM's rapid runtime makes it very suitable for multiple runs to do something similar to Monte Carlo analysis, which means that we can completely vary the sort of emission factors we're using. We can vary and move away from deterministic scenarios to include activity data, or to include less deterministic scenarios that don't include just discrete activity data. We can give the model a range and say pick between these values, take a range of different demands and everything, and we can look at other input parameters as well. So what we can do is we can calculate a mean and an uncertainty range based on this, obviously implying that a range of potential future air pollution values. So what I'm going to show on the right, just very briefly, I won't go into too much detail into it, are the sort of nitrogen oxide and PM2.5 exposure contributions from electricity generation across the time period. So this includes, we've given the model the range of the 3 net zero scenarios, and we've also varied the emission factors as well, given them sort of official numbers to work between. And you can see by 2050 that the uncertainty does get quite large compared to the earlier years. And that's predominantly due to the emission factors that we have available, that some of them that are principally used in 2050 are slightly more uncertain than those that are used currently, for example. But I also think we can do something that's slightly more interesting going forward than just looking at uncertainty analysis, which is doing something called sensitivity analysis. Now this is relatively similar, it uses a similar sort of process, but it goes beyond just telling you how uncertain everything is and telling you which of these input parameters that you put into your model contributes most to that level of uncertainty. We do this using a numerical method called Sobol indices, and these just provide a numerical value for each input. The inputs altogether add up to a value of 1, and values for each input parameter that is closer to 1 indicates that input parameter contributes more to the sort of variability of the output, for example. So I'm just going to give you a quick example here. Now we'll just have nitrogen oxide exposure from electricity generation in 2030, and then I'll show you 2040 as well. So just looking at 2030 very briefly, you can see that there are some inputs that contribute a lot more to that sort of variability than some others. Principally, if we look at the emission factors for biomass and gas, that's the extent to which nitrogen oxide is emitted per unit of energy of biomass or gas put in. They're quite important. And also the biomass and bioenergy and carbon capture and storage activity data as well, which is the extent to which these two fuels are included within the electricity generation mix, for example. So as you can see, it's relatively diverse compared to what we will show you for 2040, where by 2040, a lot of these scenarios use a lot of biomass by 2040 in order to do some carbon counting to get to net zero effectively. What you can see is that the biomass emission factor and the bioenergy and carbon capture and storage activity data remain very important going forwards for contributing to that sort of output variability, as well as the carbon capture and storage energy penalty. Now, this is sort of a parasitic energy penalty, where it's the extent to which or the amount of electricity that would have been supplied to the grid has to be put into the carbon capture and storage unit in order to make it run to capture your CO2 effectively. And there's a relative bit of uncertainty to that, which if you're having a lot of carbon capture and storage in your system by 2040, it will contribute a lot to the uncertainty. So what it's effectively doing is hopefully directing policy in a way that says this would be the most uncertain things by 2040 within the electricity system. These are the emission factors that we're using. It would be important for us to try and constrain these further and potentially have a more constrained version of your net zero scenarios going forwards as well, potentially. So I think we'll just finish with some conclusions, and then we can do some questions at the end. So as I said at the start, the decarbonisation of the UK energy system provides an ideal opportunity to improve UK air quality. There is a lot of uncertainty surrounding the direction that we can take to net zero, and these all have differing air quality impacts. We've created the CAPSAM model to assess these decarbonisation scenarios. It has a rapid runtime and takes its key air quality information from a highly validated model known as the UK Integrated Assessment Model that can give us changes in emissions and pollutant exposure across a scenario and do it very quickly again. We've just shown you some scenarios that we've done for the national grid using the national grid scenarios. They highlight the dominance of road transport decarbonisation and the importance of efficiency measures, especially in these early years. It's effectively a win-win for both the climate and air pollution improvement. And the monetary benefits from air pollution reduction is in the order of billions, but there is a large uncertainty that we need to factor in here. And then lastly, in terms of future work, we're looking to move away from these deterministic scenarios to do some more uncertainty analysis and sensitivity analysis to see how uncertain the future is across a range of different scenarios with a range of different emission factors, and also see which of these emission factors contribute most to that sort of output variability. And yeah, we can change this as the energy mix. We can investigate this as the energy mix changes to see kind of how it changes going forwards. So that is everything. Thank you very much all for listening. I really appreciate it. Thank you to the IAQM again for putting this on.
Hi Adam, thank you for that, and thanks for showing us the kind of benefits and usage of CAPSAM. We do have a few questions, but if anyone has any other questions, just please pop them in the QA function. So I'll just start with, and this was asked quite early on in the presentation, but what about aviation as well as road transport as greenhouse gas? This sector is due to expand.
Aviation is a very difficult one. There are some. For one, there are some carbon accounting issues where as soon as planes leave sort of the ground or UK airspace, they're not typically counted towards domestic greenhouse gas emissions totals. It's a slight trick. That's my opinion aside. There's also not. It's something we could definitely include in the model. There's not a lot of good information out there. You know, for road transport, we can get very discrete data about Euro-specific vehicle kilometers, and you can assess them on pollutants on a grams per kilometer basis, for example. But for aviation, it's a very important sector, as the question says, but it's not something there's a lot of information on at the moment. I think the other very important sector that the wider group looks at is shipping. The nitrogen oxide from shipping emissions, I've been told, is larger than all NOx emissions that it's around the country, I should say, is larger than all NOx emissions that's on land. I'm not sure how aviation stacks up to that, but it's something that it should be very important. But again, CAPSAM is very malleable. You can add sectors quite quickly. We have impact factors for these kind of things.
Fantastic. There's a few questions around kind of just the examples that you showed. So someone said you've considered NO2, N20 as a greenhouse gas, but why have you not considered N2 as N2 covers 78% of composition of the atmosphere, 70% of composition of the atmosphere?
Wait, sorry, if I haven't considered nitrogen as
N2.
What, as in the nitrogen, just nitrogen emissions, or
yeah.
I don't know. It's not as a pollutant that would impact human health. I don't think it's very high up on this compared to ones that have much higher and instantaneous health impacts. Particulate matter is very high on that list. So is nitrogen oxide. There are others we can include. We can produce an emission factor list for them. The only issue is that, but we don't have in UKIAM, we don't have impact factors for things like nitrogen. We have impact factors for ammonia as well, which I didn't include in the list, but that's part of the secondary formation of particulate matter, and sulfur dioxide as well. But yeah, nothing on nitrogen. I think it's relatively long-lived, so I don't think it matters too much where you emit it from, but I could be wrong on this one.
Perfect. And next asking, is road transport emissions based on the old phase-out date of 2030 or the new date of 2035?
So those will be, there were scenarios that were produced in 2021. The phase-out date changed between the different scenarios. I think the earliest that they have, the most ambitious scenario is 2030 for the leading the way, but the rest of them are 2035, or for the other two net zero scenarios.
Great. Someone's asked about what sort of uncertainty is attached to your analysis. Did you try autocorrelation analysis in your time series analysis?
It's a good question. There is a lot of uncertainty attached to a lot of this. There are some uncertainties that we can't. Yeah, there are some uncertainties that we can't calculate going forward. So the impact of a warming climate and how that will actually impact atmospheric pollution and the pollution burden in general. But yeah, so the uncertainty analysis that we're looking at is the uncertainty around the input parameters such as activity data and emission factors, and then the reason that we're doing that is so we don't look at just deterministic scenarios. We can just look at a range because they're as wide as you can pretty much get without looking at further data, which we will do, but that's not something that's happened yet.
Perfect. We have a couple of questions as well on the wider use of CAPSAM. So Ellie's asking, would CAPSAM be able to be used at local level by local authorities on local decarbonisation scenarios? And someone else has just asked, the general question, is CAPSAM model available for us to test?
So CAPSAM, I should have said, it's on a national basis. So we can do it's for full decarbonisation scenarios of the UK, but we can make them slightly smaller in terms of we can do so DAs, so we can do England, Scotland, Wales, Northern Ireland as well, but we haven't done that yet. But yeah, the impact factors are on a national basis alone. I'm not sure. I don't know how it would work for local government because I don't know if they'd be in charge of their decarbonisation policies to the same degree as full energy system models would require it to.
Okay, perfect. Gareth's asking, have you considered monetary benefits from air pollution reductions on ecosystems?
Yeah, so the other environmental benefits that I showed, if I can go back slides, this slide down here, sort of the other environmental benefits that we have for road transport is predominantly due, this is in the negatives, due to the removal of what's known as free fertilizer from nitrogen oxide emissions. As we're putting sort of nitrogen-based fertilizers on the ground, this is something that can be sequestered by soil. It's effectively what's considered free fertilizer. Now, there's a lot of uncertainty to this. So the numbers can change quite a lot. We have a consultant that we work with who's part of the Committee of Medical Effects on Air Pollution, who does these numbers, and there is a lot of uncertainty to them. In terms of the rest of the ecological benefits, I typically just work within the energy system. So we have another project or another PhD student that does a lot more in terms of the agriculture side of things.
Just while we've got this slide up, someone is asking if you could explain a little bit more about the Defra discount rate with the 3.5%. Yeah,
so the discount rate is applied kind of on a year-on-year basis. The value is from the Treasury's Green Book. I don't know if the person that's asked the question is aware of it, but it's effectively money in 2021 is more valuable than it is later on in time, in sort of like in line with inflation. Again, 3.5% is potentially quite optimistic, but it just means that the savings that you make year on year will be 3.5% less important than it would have been the year before, which is why it's designed to reward savings that are made earlier. Because if I had £100 that was in 2021 money, it's worth a lot more by 2050 than it is now, if that makes sense.
Yeah, perfect. And the last question from Gordon is, are you aware of any air quality or greenhouse gas model for new residential developments, which many IAQM members work on, micro scale relative to CAPSAM? I'm
not aware of any of those. I'd happily love to get some more information on those kind of things. In terms of, I think it would still work with the impact factors for domestic heating. I think would still work because depending on what part of the depending on if it's on a gas grid or not, you have different impact factors for different types of heating. So the impact factor for domestic heating of wood is typically in a lot more rural areas. So you can still apply a domestic an impact factor for a new sort of settlement in town because it's still a sort of there's still a relatively similar distribution of people surrounded by these emission sources, if that makes sense.
Perfect.
I also think I missed a question on if it's be available going forward. It potentially will be at the end of my contract with Defra. This is hopefully a model that we can publish going forwards, but not currently yet. I'm trying to get a paper out on it that sort of validates it in the eyes of publishers going forwards. But yeah, it hopefully should be available at some point in the future.
Fantastic. Thank you, Adam. Thanks for a great presentation and thanks for answering all those questions.
Thank you very much.
And that is it from us today, attendees. Thank you for logging in. I hope you found it beneficial and informative.